Well, it is always a pleasure to welcome a former student from the IEC, as Teo Muñoz. Teo was a student, a PhD student here. He did his PhD mainly on optical studies of X-ray transients, with emphasis in high time resolution. And correct me if I am wrong, you submitted your viva in 2008. And then after that, you enjoyed a Marie Curie postdoc fellowship in Observatorio di Brera for 2 years. And after that, you moved to Southampton. And now you are with another Marie Curie. They are working with Rob Fender, Phil Child, and the X-ray binary group there. So it's a pleasure to have Theo here, and he's giving a seminar on X-ray binaries.
Okay, I think it's working. So, good morning, everyone. Buenos días, todo el mundo. It's for me a real pleasure to be here. I started my career here at the IEC, and when I'm here, I feel at home. So, I mean, let's see if you enjoy. If you enjoy half an hour talking about black hole X-ray binaries. I want to give you a brief overview about the outburst evolution of these systems. I want to show you how interesting, how exciting is the physics that we can learn when looking at these binaries. And in the last part of my talk, I'm going to present a new paper. It's actually today on AstroPH, in which I focus on the general relativity effects that we can actually detect when looking at black hole X-ray binaries. So the black holes that we know in the galaxy, the stellar mass black holes, are found in what we call low mass X-ray binaries. Low mass X-ray binaries are X-ray binaries in which we have a solar-like star, which is transferring material onto a black hole or a neutron stars. The two bodies are rotating around the center of mass of the system, and for these reasons, when the matter is transferred, it carries also some angular momentum. And in this way, an accretion disk is naturally formed. So here we say that the mass transfers take place via accretion disk, and due to the strong gravitational potential that we have very close to the neutron star and very close to the black hole, and also due to the viscous nature of the disk, the inner parts of this accretion disk become really hot, and these systems can be really strong X-ray sources. On the other hand, since we can study the behavior of the matter very close to the black hole on the neutron stars, these systems offers us very nice potentials to study black holes and neutron stars, and in this way, there are very good neutron star and black holes laboratories. In other words, there are, let's say, extreme physics laboratories. So, one of the main properties of black holes X-ray binaries, from now I'm going to focus on black holes X-ray binaries. They share many properties with neutron stars, but in this talk I want to focus on black holes X-ray binaries, which is my expertise. So it happens that whereas most of the neutron stars are found in persistent systems, persistent means systems that are always active, that you always detect them when looking using X-ray telescopes, black holes tend to be observed in transient binaries. I would say that 90% of the black holes that we know are found in transient systems. And by transients, I mean that they spend more part of their lives in a dim, quiescent state, in which the accretion disk emit very few in X-rays. Actually, to detect one of these guys, if they are not far away, we need a very deep channel observation. You need several Chandra kiloseconds, because the luminosities are of the order of 10 to the 30, 10 to the 39, 10 to the 31, sorry. And due to the fact that they have dim disk, we are able to detect all the components of the binary. So if we do a spectroscopy in the optical, we are able to see the disk, but we are also able to see the companion. And if we see them, we are able to trace their movement. So by tracing the movement of the accretion disk, and especially of the companion stars, we are able to perform dynamical studies. So when their systems are in quiescence, they are very good and they are very interesting for many reasons, but especially because we are able to perform the dynamical studies. And this is actually one of the main expertise of the X-ray binary group here. I did the PhD essentially in this topic with Jorge, and using these techniques, and these techniques relies essentially on the Kepler laws. So you just measure the movement of the components and apply the Kepler laws. We have confirmed the presence, dynamically confirmed, the presence of about 20 black holes in the galaxy since the first convincing evidence by Jorge in 1992. So you can see here, these are compact object masses, and these are, several systems that we actually found a group of systems above 5 solar masses. There is no equation of state for neutron stars that allow a compact object to be as massive as 5, and we call them black holes. On the other hand, we also have a group of systems around 1.4. They can be as massive as 2 solar masses. And interestingly, there is a gap here in the distribution that, although the errors that we have, the uncertainties that we have are large, this gap here is insignificant. So this is, and tell us about, for instance, the supernovae explosion models, tell us about the last stage of the evolution of very massive stars. So the study of the distributions of masses, of compact object masses, is actually very interesting for different aspects of the modern astrophysics. But today I'm not talking about this thing. I'm going to talk about system being in outbursts. So they spend most of their lives in quiescence, but every year, every decade, every century maybe, they go into outbursts. And when they go into outbursts, the luminosity, the X-ray luminosity of these systems increase by 6-7 order magnitudes. So we have a system that is barely detected with Chandra, and suddenly we observe the system with just a small X-ray monitor. So because the increase in luminosity is really large, and this system have very bright accretion disk because the matters, the transfer rate increase a lot, and the matter gets really close to the black hole. And for this reason, they are excellent laboratories to study accretion processes. Since also the gravitational potential that we have very close to the black holes are huge, and the velocity of the matter of this accretion of the matter in the inner parts of this accretion disk approach the speed of light, we can also study general relativity effects. So from now, I'm going to focus on this epoch when the sources are strong X-ray sources. So this can be a picture of a black hole in outburst. We have several spectral components. We have a very bright accretion disk that emits from soft X-rays. By soft, I mean 1 or 2 kV to the infrared. We also have a corona. We see hard X-rays that can be modeled by a power law. This accretion disk is thermal, whereas this corona can be modeled by a power law, and we believe that this corona is the result of having a cloud of electrons that up-quantize seed photons coming from the accretion disk. On the other hand, we also have a companion star that sometimes can be seen through X-ray reprocessing. So we can see this part of the companion that is illuminated by the X-ray photons coming from the X-ray source. And also, for some particular moments, for some particular accretion states, we also have powerful jets that we detect in the radio, in the infrared, maybe the optical, and it's quite controversial if we detect these jets also, these jets also contribute to the high energies, to the X-ray flux that we'll see. And I will talk about this thing later. So as it's clear that we have several spectral components, these systems, these binaries are multi-wavelength sources. So in radio, as I showed you before, we have the jet, not always, but for some particular states we have a jet. In radio, it dominates also in the infrared. From optical through X-rays, we have the accretion disk, this thermal component, thermal accretion disk component, and here we have the corona, where the photons coming from the disk are up-quantized towards energies approaches 100 keV, even 1 mega eV. In the talk, I'm going to focus in this part, because in this part we see major changes in the timing and the spectral properties of these sources, and these changes led to the definition of X-ray states, but I will show you how these X-ray states are also connected with other properties, like the presence or absence of jets, or like the presence of absence of strong accretion disk winds. So in order to study the outburst evolution of black holes, we essentially use this diagram. What we call it is it's quite technical, but we call it hardness intensity diagram, and it's a very simple diagram indeed. So we plot the count rate, which is for you is X-ray luminosity, as a function of an X-ray color. An X-ray color is we just take a hard band and we divide the flux in this hard band by the flux in a softer band, and we take a color and we plot here X-ray luminosity as a function of the color. So what we see at the beginning of the outburst is that the outburst starts here. So we observe a rise from the quiescence, and during this rise, we see that the X-ray color is very hard. So we call this part hard state because, the X-ray color is hard. We see a fast increase in luminosity, and at some point, we see that a transition takes place. And it's important to mention that every point here corresponds essentially to one observation, to one XT observation, and we essentially have like 1 point per day. So you can see how in 1, 2, 3, 4, 5, 6 days, the system moves from being hard, from being dominated, from having a hard color to having a soft color. And this is quite important because when the system reach this soft state, it can be stay there for 1 or 2 months, whereas this transition just lasts a few days. Here we are dominated by the hard component, and in this part we are dominated by the accretion disk component. In this part we see that vast majority of the light is coming from this thermal accretion disk. During this soft state, the luminosity decreases until reaching more or less 2% of the Eddington limit, and when the flux is that, so 2% of the Eddington limit, we see again a back transition toward the hard state again, and the system returns to the quiescence, following essentially the same path. Since the system moved from hard to soft and then from soft to hard using a different path, we call this diagram a hysteresis diagram. It's also interesting, I've been talking about colors, I've been talking about luminosity, but it's also interesting that the properties of the variability change also. For instance, when the spectrum is hard, so at the beginning and at the end of the outburst, we see a lot of variability. I mean variability, when I compute variability here, I'm meaning variability above 1 Hertz. So time scales faster than 1 second. So in these time scales, we see a lot of variability, and with the system is in this dominated state, in this soft state, we see just 1% variability level, whereas here variability can be even 50%. Actually, if we just focus on the variability, and this is a paper that we published a couple of years ago, we also find this hysteresis diagram. So here I just plot luminosity and variability for the same source for 3 outbursts, and we see that we always find these tracks. So this track here corresponds with a lot of variability seen, correspond again to the hard state, so dominated for this hard emission, and this here this track here where the availability is as low as 1% correspond to the soft state, and these kind of loops are repeated by the black holes every time they go into outburst. Also, it's worth mentioning that there are other state-dependent timing features that, like quasi-periodic oscillation that we know happen at very particular phases of the output. For instance, we have QPOs in this area, but we don't have QPOs in this area, for instance. So there are many things that can be connected to these X-ray states that we believe are actually connected to different accretion states. So focusing a little bit more on the physics of these X-ray states and not in the phenomenology. So on this part, what we believe that we have is this corona of hot electrons that is upcontonizing photons coming from this disk, but the disk here is very cold and probably is very far away from the black hole. However, when we move to the soft state, we have the system dominated by this thermal disk component, and we believe that here the disk is not truncated, but the disk moves all the way into ISCO. ISCO is the inner most stable orbit that allows by the general relativity. So actually the system configuration, so the accretion regimes that we are tracking change dramatically from one state to the other in time scales of just 10 days. But all what I've been talking before was related to X-ray observations. However, the radio jets, so the radio emission, so the opposite part of the spectrum is also very well correlating with these X-ray states. For instance, we see a strong compact jet when the system is in the hard state, so when the system is dominated by this high energy emission, and actually this radio emission is tightly correlated with X-rays. And this correlation is not only observed here in black hole binaries, it's also observed in AGNs, and it's also observed in neutron structural binaries. So this is a universal correlation that seems to link accretion and ejections events. At some point, when the system starts to move soft, we see that this compact jet start to be weaker, but in this area, we see how instead of having a compact jet, optically thick compact jet, a slow jet, if you want, we suddenly see a strong relativistic ejections. We saw here in this area, some people call this area the jet line. So in the middle of the transition, we saw this relativistic ejection. We see powerful jets moving at relativistic velocities. And when the system, let's say, stabilizes and is dominated by the accretion disk, we don't see the jet. And actually, there is a very nice paper by Dave Russell. He was here, but he's not in this room. And actually, he proves using really deep observations that the jets are not present in this soft state. So this X-ray emission are tightly correlated with radio emissions. And the nice thing now is that all these discoveries have been performing in the last 15 years, and what I saw before is mainly observation of one system, which is the famous one, the one that behaves better if you want. But XTE has been observing many of these black holes in the past. And for all of them, you can see here again luminosity as a function of the color. We have seen these tracks. But the tracks are not exactly equal between them. You can see here this track in purple corresponds, again, one observation is 1 day. We have every color correspond to a different source. And we have here, so these purple tracks, these red tracks, these yellow tracks. So, the global thing, they do the same thing, they do these loops, but it's clear that there are some difference between one system, between the different systems. So, since the data set is large enough after 15 years of the mission of this satellite, people start to think on systematic studies and want to understand the difference between the different systems, the different behavior between the different systems. And one nice thing to do is, for instance, compare the behavior of high inclination sources, so sources that are seen edge on, so this is the orbital place, this is the disk, and this is the companion. Difference between sources that are seen edge on and sources that are seen face on. So sources that we have this is the orbital place, and we have the accretion disk here. So in 2012, Ponti and collaborators presenting this study. Here you have the same diagram for high inclination and low inclination sources, and what they wanted is to check whether accretion, winds from the accretion disk are present or not in the systems. So these are the tracks I was talking about before. The circles means the detection of absorption lines that in X-ray absorption lines that are interpreted as coming from accretion disk winds, and triangles mean non-detections. So at high inclination, and when the system is soft, they detect these accretion disk winds, whereas at low inclination, they don't detect any wind. So this is quite interesting because, they compare the whole population of black holes, not the whole population, but 10 systems, and this suggests that these winds could be ubiquitous, and indeed, it could be that they represent a new ingredient in the outburst evolution. So it could be that when we don't have the jet, we have the wind. It's actually a very nice and new study, and people is quite excited about this thing. So, for instance, are these winds sweeping away of the matter that goes into the jet, or are these winds always present, but we are not able to see them in the hard state because the matter is really ionized? So this seems a new and exciting ingredient in the accretion picture. Also, these people realize, and chatting with them, we reach the conclusions that the shapes of these tracks seems also to change with inclination. And this was done for 8 systems, but was something that we wanted to explore in detail, and is the paper that is today in Astrofísica, and I want to talk about here, and which talk about the different black hole evolution that we see depending on the line of sight, depending on the orbital inclination, depending if we see the black hole edge on or if we see the black hole face on. So let me show you again this boring picture, which is quite important for my talk. Just remember one thing, that in this part of the diagram, so at the beginning and at the end of the outburst, in this hard state, we don't see the disk. So we only see a hard energy component. And in this part of the diagram, the system is dominated by light coming from the accretion disk. So if we want to compare two population of sources, low inclination sources and high inclination sources, the first thing is to plot them. So here I show you a very good example, actually the example that I've been shown during the whole talk, which is GS39-4, is a low inclination source. Again, luminosity as a function of the color. And in the bottom panel, I show you another system, this telephone number, 1655-40. And maybe you notice that the transition here are quite horizontal, whereas here we have this triangular shape. Also, you might realize that this system becomes a bit softer than this system. So the color is a bit smaller if you want. But this can be just by chance and just by the fact that I pick up two sources that behaves in a different way. However, if we plot the whole population, we see that this is actually a global trend. So here, all the transitions are horizontal, as you can see, and here, let's see like triangles. More interesting, every low inclination source becomes softer than the whole population of high inclination sources. And the question is why? Why we see this clear trend here? So let's think about as I was mentioning before, in black hole binaries, so the matter is falling to the gravitational potential of the black holes. Matter is moving close to the speed of light. So general relativity becomes important. So let's see that the effect that general relativity could have in this accretion disk. So when we are seeing an accretion disk at low inclination, so like this, we are of course dominated. So we have the disk, the emission from the disk, normal emission from the disk, but this is affected by gravitational redshift. It's affected by the fact that the photons that are very close to the black holes, they see the time interval shorter than we do. At high inclination, when we see the disk like this, of course, gravitational redshift is also present. But I'm going to show you now that we also have blue shifting effects that compensate this redshift due to the gravitational potential. So in this plot, I show you the disk, an image of the disk in projected coordinates. And so the matter here is rotating anti-clockwise. So in this part, we have, let's say, we have a redshift, and in this part, we have a blue shift. And the central part is dominated by the gravitational redshift. However, matter in this area is moving at half of the speed of light, and for that reason, we are having here Doppler beaming. Doppler beaming means that that light tends to be emitted in the direction of motion. So we are seeing much more light coming from this part of the disk because of the Doppler beaming than light coming from this part of the disk. So when we see the disk like this, when we see the disks edge on, we are having a net blue shift effect that is going to compensate, in part, the gravitational redshift effect, but only for the systems that are seen edge on. On the other hand, you can see here that if the matter gets really close to the black hole, we are also having light bending effects. So the matter that is coming from, let's say, behind the black hole start to cube towards the observers. So this is going to compensate also the different projected area of the disk with inclination. Because when we have the disk like this, we are seeing also this part of the disk, this light is enhanced because light bending effects. And in this has been predicted by very detailed accretion disk models. Let's focus first at the bottom panel. Here you see the spectrum. So this is observed energy, and these are number of photons. So a spectrum of an accretion disk as a function of the inclination. 0 means face on, close to 90 means close to edge on. So you can see that at 90 degrees, the disk becomes hotter, so blue shifted, than at 0 degrees. Another important, 0 degrees, which will be here. Another important parameter here is the spin. The spin is a dimensionless parameter and tell us about how fast the black hole rotates. And interestingly, from this problem, the spin regulates how close the matter gets to the black hole. And of course, if the spin is very large, so if we have a curved black hole, a maximally rotating black hole, the matter can get really close to the black hole. And if the matter is close to the black holes, this relativistic effect become more important. And it's what we see here. So as the spin grows towards the curved black hole, we start to, the blue shift effect is higher. So let's say that the disk looks hotter just because of general relativity. And the question is, do we really see this thing? So do we really see that disks are hotter when seen at high inclination? And the answer is yes. So here, using the same data that I saw before, I plot the temperature of the disk for the low inclination sources and the temperature of the disk for the high inclination sources. And you can see how the difference is really evident. It's a factor, is 50%, can be as 50% larger. These temperatures are computed using simple Newtonian disk models that they don't take into account these general relativity effects. So in order to have the real temperature, we should correct them by few terms, one of them depending, as we saw before, of the general relativity. And in particular, it depends on the inclination and on the spin. So we can actually apply these terms that are tabulated in papers from the 70s, actually. So this is very well-known physics. And when we apply a zero spin correction, so a correction, so this will be, let's say, the minimal correction that we can apply, we can see that this temperature move slightly to higher values. But still, there is a discrepancy between these two populations. We can actually also apply the maximum correction, and we see how now it seems that, I mean, the match is better, but it's probably, this correction is probably too much. But in any case, I mean, of course, we don't know the spins of every system, so it's impossible to do an accurate match. But it tells us, I mean, that is this factor, is this general relativity factor, the one that we need to reconcile the two populations. And actually, we can do a much better thing. We can actually fit the whole outburst evolution from the two systems. So this is a low inclination system again, and this is a high inclination system. We can fit the whole outburst evolution within a full relativistic model. And these full relativistic models, one of the parameters that includes is, of course, the inclination. So if we fit them using the inclination, the real inclination, 40 degrees in red here, the field dots, we have what we had before, so the same, essentially the same track. And here, in blue, for the high inclination system, we had what we had before, in blue. But since this is since inclination is now a parameter, we can actually freeze the whole spectral model and change and switch the inclination from low to high and vice versa. And here, when we switch from 40 to 70, we actually see how the system gets harder. And here, when we switch from 70 to 40, we see how the system gets softer. So it seems that the whole thing works, and actually the outburst evolution that we see is actually modulated by general relativity effects. Could be also other factors, because maybe you realize that, I mean, for instance, another difference was that these transitions were horizontal, whereas these transitions were more triangular. This part, applying the correction, seems more horizontal, but the shapes are not still quite the same. So maybe there are other factors. For instance, now I am applying correction to the accretion disk component, but we also have this corona component, this Comptonization component that can suffer also of viewing effects of general relativity effects. But as a whole, I would say that, I mean, that the general relativity explains much of the phenomenology. So I'm actually finishing now. So I hope that I show you that the black hole binaries are quite exciting. They are I would say, fundamental physics for compact object physics, but also for they can act as extreme laboratories for extreme physics. They are able to provide dynamical black hole masses. So all the dynamical black hole masses that we know are coming from these systems, and they are able to provide detailed accretion studies in time scales that are adequate for human beings. In the last part of my talk, I saw that the observed Outburst evolution depends on the inclination. Indeed, the black holes that are observed at low inclination look softer, so it looks cooler if you want. And this discrepancy can be explained just invoking very simple general relativity effects. And I'll leave you with this slide in which you can see in a much more detailed way the different tracks of system at low inclination and at high inclination. Thank you very much.
Okay, thank you very much for your talk. So now it's time for question.
I have actually two short questions. The first one is about this explanation of the difference of temperatures and the variation with inclination. You didn't mention any radiative transfer in the disk, so they are transparent to X-rays, the whole disk, or this gonna? I mean, forget about that you are dealing with X-rays. If you were observing the disk in the optical, of course, it's not the same. I mean, you have a lot of opacity, so it's not the same whether you see them face on or edge. Okay. So is the same effect taking place in X-ray, or everything is transparent? I guess you're saying that the disks are transparent for X-rays, right?
I mean, when first of all, when I mean disk, I mean just the really inner part of the disk. So I'm not talking about the whole disk. That is, I mean, the outer part of the disk are emitting actually in the optical, and they process X-ray emission and are emitting in the optical. I'm just talking about the matter which is really close to the black hole. So any of this system is actually edge on. So when I mean edge on, I mean like this, and you are actually always seeing the X-ray source. So,
but if it is really edge on,
but
in other words, this is big enough, even if it's not perfectly edge on. In principle, you will have this right.
Yes, I mean, in
some of the photons won't come directly towards you. They will be absorbed by the display, they absorbed by relativistic.
Yes.
So, is this effect important? That's my question.
At this inclination, no. I mean, because I mean the inclination here are about 70 degrees, and at this inclination, no. And actually, I mean, of course, I mean this study is much more complex than that. We of course we correct from different absorptions that we see. So all these fluxes are not fluxes as they are observed. So they are corrected from the absorption than we see and so on.
And the second short question is about what hits the corona?
What hits the corona?
Yes.
So we think that the presence of the corona is not well understood. So that's the first question. But I mean, we think that this cloud of electrons here is actually hit by the strong emission that is coming from the accretion disk.
So, but then I didn't get the point. Maybe this is again a very naive thing. But if you're saying that the very hard X-rays come from the corona,
yes,
which is hotter than the disk.
Yes, in the
corona,
you
have to manage to heat something at a temperature that is higher
than
the temperature of the disk.
But the corona, the corona is an optically thin media. It's like the let's say like the corona of the sun. And it's not well understood how it's heat, but what we think that understood is how these electrons that these photons that we observe at 1 kb are converted in photons at 100 kb. So, and there are few observables that suggest that this corona of hot electrons, optically thin corona of hot electrons is present there, but how this corona is formed is not well understood. For instance, some groups think that this corona is actually the base of the jet and is related to magnetic fields, for instance, the presence of this cloud of electrons there. But the formation of the corona, the geometry of the corona is not understood at all.
Thank you.
Okay, so more questions?
Thanks, Theo, for the nice talk. Is this working? Yeah. I have two questions. One is if you have explored alternative explanations to this difference between high and low inclination. So, for instance, using different fraction of upscattered, of Compton upscattering, right? That's something that would come to my mind, like as a trial. And the second is about this diagonal track in the high inclination systems, right? I think, if I remember properly, it's what some people have called ultraluminous state. Or so, what the question would be, if you have some physical scenario to explain this state that happens only in high inclination systems.
First question, starting by the second question, I don't have any physical scenario for that. But, I mean, this ultraluminous state is in 1655, is this part, actually. So I'm not only talking about this part, which is the ultraluminous state, I'm talking about the whole thing. So actually, here, for instance, you can see that here we see like a vertical drop where once the system is in the soft state, and here the system, or here the system approach the soft state, and actually when it reached its minimum luminosity, we see again the transition. But I mean, this you can argue, and at the beginning we found these things that are just shapes. What is interesting are, I mean, the different colors and the different temperatures, which actually what is leading the result. And talking about the different possibilities, is actually the possibility that I explained now is the last possibility that we thought about. So at the beginning we explored different fits also for the hard component, but there is no convincing result. For instance, we see similar power law normalizations. We see similar photon index for both population. At the beginning we also thought, which is actually connected with what Jorge said before, we thought that could be just the absorption was different for both systems, because absorption can cause this. So if you have if these systems, if the high inclination systems are more absorbed for any reason, intrinsic absorption, what we see is that the flux gets harder and the dark flux gets softer, gets fainter. But so we try to fit the whole population using higher absorption values, but the temperature remain the same, remain higher for the high inclination sources. And on the other hand, now that we have found this, if we wouldn't have found this thing, would be quite strange, because those corrections are applied by people when they want to build up models from the backward evolution in the 70s. So it's actually, this difference that we see is something that is expected. So to see this difference in temperature is not strange, although we never realized before, because we were not comparing the whole population of systems. But I mean, it would be really weird, and if we don't find this difference in temperature, for instance, it will be quite weird, because those corrections are there since the first models in the 70s.
Okay, some more questions?
Is there any relation to the mass of the compact object for objects with the same inclination? I mean, the luminosity, is it related to the mass of the compact object?
So the mass of the compact object, the mass of the black hole is going to change the temperature. So the first thing we explore, and actually one of the main assumptions here, is that the two population of systems are the same, but what is different is only the orbital inclination. So the mass of the black holes for the high inclination systems change between, let's say, I think it's between 5 and 10, but the same is true for the low inclination systems. because of course, yes, there is a weak dependence. Well, not that weak, but I mean, in one order of magnitude, there is a weak dependence between the disk temperature and the mass of the compact object. That's true, but I mean, it's not what is leading this thing. There? Yes. Yes. The spin, I mean, the spin is able to change the disk temperature by a factor of by 50%.
Okay, more comment or questions? Okay, so there is no more questions, so let's thank again our speaker.